Today, we have the pleasure of introducing Ron Taylor, who probably some of you have had in Comp 150. I'm going to read off his sort of resume a little bit. He got an A.B. in mathematics and physics from Wilmington College, which is just south of here. He received his MS in mathematics from Wright State and his PhD from the School of Engineering at UD. He conducted research in software development as a physicist and an aerospace engineer at Wright Air Force Base. But he spent most of his career teaching mathematics, applied mathematics, I should say, and computing at Wright State University. He retired last year from Wright State, and now he's with us here at Wittenberg as an adjunct instructor, teaching Computer Science 150. And I should also mention he is also an instructor with the Greater Miami Valley Computer Science Circle. So he's going to talk today about computational science, the pitfalls of computing. As I mentioned, this is more sort of an application area of computer science, which should be very interesting because it's useful to sort of see how computer science is being used in applications. So, Ron, take it away.
So we'll see some pitfalls, we'll see some disasters, we'll see some good things, and things with numbers, and things with actual physical structures, and some airplanes, and bridges. Well, a lot of different things in this presentation. Let's see. Computing is fun. I like computing. It's important. I think we all know that sometimes computers don't behave too well. Although, you know, Bill Gates once commented that comparing a computer to a car, if GM had kept up with technology like the computer industry had, we would all have cars that cost $25 and get 1,000 miles per gallon. General Motors kind of responded to that, and it said the following. Go here. Your car would crash twice a day if your car was like a computer. What else would happen? Occasionally your car would die on the freeway for no reason. You pull over the side of the road, close all the windows, shut off the cars, restart it, open the windows. For some reason you would think that was okay, that's kind of the way things were supposed to be with your car. You'd have an oil, water temperature, and alternator warning lights. They'd all be combined into one light. It would just say, this car is performing an illegal operation, and the car wouldn't work. That's all it would tell you.
It's kind of like the check engine light now.
Check engine, yes, that's right, yeah. Occasionally your car, for no reason, for no reason whatsoever, your car would lock you out, refuse to let you in until you simultaneously lifted the door handle, turned the key, and grabbed a hold of the inside. Finally, my favorite is the airbag system would ask for frustrations that occur with computers and computing, that's for sure. Okay, so we're going to talk about a couple of major areas here. One is just kind of computational science in general, get a little bit specific for some of the things that's been happening over the last 10 years or so in the area, academically and with other schools even. We'll talk about disasters, both numerical and actual physical ones. The one example here is just an algebra problem. It's called the rump function, R-U-M-P, rump function. And here it is on the board. It's just it's got some X's and Y's in it. And I guess the only place where it's doing a division is right here. It's X over 2Y. Compute then what that is. Right? And you'd be surprised how hard that is. It's kind of an amazing problem. We get into some very interesting computing issues. We'll look at an algebra problem involving square roots and how to simplify that to make it perform better numerically. We'll look at a calculus problem involving a series and how to make that better numerically. And a little bit of comment about statistics when we have widely varying numbers. What's the best way to add up numbers? And end with a summary and questions. Okay. that's the agenda. As far as references, if anybody wants any of these, I do have them. Just send me an email. I could send you PDFs. I did a couple of what I call computational science modules I developed. It was under an NSF contract with, actually it was through Capital University. But the money came initially from the National Science Foundation. So two of those modules, there was a third one we did, that's not on this list. Goldberg's paper on what every computer scientist should know about floating point arithmetic, somewhat older paper, but has a title that somehow beckons us to look closely what he was saying back then. One of my favorites is Pitfalls in Computation, or Why a Math Book Isn't Enough. We'll see a couple of examples there that might indicate why that could be a conclusion. And then also we'll look at the Leclerc summation of how better to compute that thing called the Bruck function. Okay, so what is computational science? Or maybe stick with the word engineering, let's just call it CSE. What is that? A typical presentation on what it is would involve mostly three circles: a computing circle, a mathematics circle, and a disciplinary circle that overlap like a Venn diagram. You plug in what your discipline. Are you interested in biology, chemistry, physics, applied math, you name it, engineering. The overlay I put in there, kind of my take on this, was the importance of communication. It's not just enough to compute or understand your discipline, but being able to bring all that together in a consistent, coherent manner and explaining it to others. Collaboration, communication, as well as these other areas are very important. Writing for a mathematical discipline, that could be different than maybe writing for a computing discipline. Each discipline has its own standards of communication. One thing I think that is important, the last one, all things are important, but consistent use of visualization and documentation. Define the terms, define your charts, make sure that things are done in a consistent and even manner, depending on your discipline. As far as tools that computational science uses, a lot of times we'll be using, we'll say, canned routines, things we get from various sources, and some of them are very good sources. One that I've used over the years is MATLAB. For those of you in physics, I think may have used MATLAB or will use MATLAB. It tends to be kind of an expensive software package, and not everyone may have access to MATLAB. A number of years ago, I was approached by a sponsor who said, suppose there's something heavy in a trunk of a car, and we want to detect if that's really, is there something locked in the trunk? They didn't really explain what that was. I kind of suspicious what they were talking about. But their question was, could you send a car over a couple of speed bumps and tell, just based on how it was bouncing, pitching and front end coming up, back end going down, how it was oscillating? Could you tell if there really was something in the trunk? I remember I worked rather hard on that. First they wanted it like the next week. I don't know. But I used the MATLAB a differential equation solver, ODE 4.5. I hurried up and did it, and I got an interesting result. I started the car like 500 feet from the bump, and I did a time step, and it was going at a constant speed. And absolutely nothing happened. I was looking for acceleration of the center of gravity. Nothing happened. Tried it again, a bigger bump, maybe the bump was too small. Bigger bump, nothing happened. I could not get what we thought was a really, really good numerical routine, the rugged cut solver that was in MATLAB. Could not get it to do anything, just zero. So I looked at the equations, the equations were fine, the coding of the equations was fine, but nothing happened. Then I thought, I guess I'd better read the documentation on the integration procedure for these equations. And it said something about an adaptive step size.
Yeah.
What it was doing, if you started the car too far away, it said, okay, nothing happened the first step, I'll double it. Nothing happened the second step, I'll double it. I'll just keep doubling the step, and by the time it got to the bump, it stepped right over the bump. We didn't even see the bump. So Okay, lesson learned. What I did, I went ahead and coded my own routine, and then I finally got MATLAB to work. But it was nice coding my own routine. I understood what was in it. I understood the math, I understand the computing, and it did compare rather well. So even though the routines are available, be it MATLAB or other sources, it's still good to code your own because you understand what you put in your own code compared to then maybe the better software. But read the instructions, I guess, would be the lessons here on that. I finally got it to work, and I turned it into a sponsor, and never heard a thing more about it. That's kind of the way things go sometimes. You do the job, and if it's maybe a sensitive area, you just don't, you never know. I guess no news is good news. Anyway, the computational science modules is not the car. Well, the car bump was one that I did turn into a module, but 7 or 8 years ago, we did have kind of a consortium of schools in Ohio, Wittenberg, Ohio State, Wright State, you name it. It was quite a good group there, and the work was done under National Science Foundation sponsorship. So we came up with a couple of computational science modules. This is kind of a little bit about them. It was supposedly for computing, maybe mechanical engineering might be important, but there was it kind of was an upper level course that engineers certainly could enjoy working on. I called it the Analysis of Damaged Panels in Supersonic Flow, kind of a strange title here, but I'll show you why it was important. Sometimes things fail. Here's a bridge falling apart. Tacoma Narrows Bridge, 1940, fell apart. The wind caused the problem. The wind kind of caused the main section, it was a 2,800-foot main section of the bridge. The wind kind of lifted it up a little bit, and it tilted it. And the tilting caused it to lift more, and it got into this, you might say, a vicious cycle where the lifting caused twisting, and the twisting caused lift, and the whole bridge fell apart. You might say, well, it must have been almost a hurricane or something, you know, a couple 100 miles an hour to make a bridge of that size. It was 40 miles an hour wind gusts. I think the engineer was unemployed after that. But the thing that they forgot to take into account was the fact that there was a significant wind. You know, well, 40 miles is not too bad, but it was just the construction of the bridge did not take into account this important factor. So showing relevance, as a teacher and researcher, we're trying to indicate to students why something is important, show some relevance. I think that in real problems can be quite challenging. Here's another problem. Back in World War II, the V-2 rocket, I don't know if anybody knows the history of World War II, but the Germans had a V-2 rocket that hit London, and it would have done a lot more damage had they been able to fly more of the rockets. The fuselage part of the rocket, this is on the right side from the inside out. The panels kept failing, blowing off, or some type of failure. It turned out to be a flutter condition, just like the bridge. It wants to oscillate. These panels had an oscillating problem. Similar problem occurred with an airplane you may have never heard of, the X-15 rocket plane. Been about 50 years since they've flown that. 4,500 miles per hour, still the fastest speed of any aircraft ever. It could go up to 67 or more miles. It would gain altitude about 1 mile a second. That's moving out. Could get it up to the edge of space. I think the altitude record has been surpassed here. But it had problems with panels on it. The shaded areas where the panels would fail and fall off, that's not what you want for an airplane. So why did that happen? One of the things we did in the computational science module was to get a small piece of a panel, just an analytical model. Coordinates, which way is up? A lot of times in aerodynamics particularly, it's hard to agree on a right-handed coordinate system, and getting couldn't get the coordinate system correct and the geometry, so made some simplifying assumptions. This geometry led to, well, I'll show you the equation in a minute, but I did encourage the students to think about not just the model, but think about broader questions. You know, what was the history of the World War II? What were some of the importance of high-speed flight vehicles, the V-2 rocket, and so on? One of my favorite questions here came up apparently. Someone attributed this to a certain scientist. He says, once the rockets are up, who cares where they come down? Well, that's not my department, he said. Sometimes you can get so blinded by a problem you forget about there's a broader context for what you're doing. Anyway, that was a famous scientist, worked in rockets during World War II and then the space program for NASA. I want to see if you can find out his name. Back to the specifics of the panel, it turned out to be a partial differential equation. Well, how that developed is really not important here. But understanding what each term was, the so-called forcing function on the right-hand side, what it included, how do you interpret those from an application standpoint. There was a pressure force, an edge force, a foundation force. Understanding what each term in the equation means. It's not just in a differential equations course, you'll solve equations as you should and get solutions, hopefully analytic solutions. In practice, almost every single term means something, and it has a dimension to it, a physical dimension. Understanding the dimensions and the consistency of the dimensions is really, really important. Let's see what we can do here. This is the diagram which kind of shows the instability that occurred in the panels. It's a relatively simple looking diagram, but there's a lot going on to it. You see some blue lines going up vertically. They start at the horizontal axis. Where they intersect the horizontal axis, there's points across there. 1, 2, 3, 4, 5. This is a non-dimensional scale, but they represent the natural frequencies when there was no air blowing. You know, things tend to vibrate. You know, if you pluck a string, it vibrates in one piece or two pieces, three pieces. There's frequencies associated with these elastic panels that we use to construct the V2 to the X15. As you increase the velocity of the air over it, those frequencies change, and an interesting phenomena occurs. The first two natural frequencies merge into a common value. And any air velocity above that common value is unstable. It's an eigenvalue problem, a matrix eigenvalue problem. When you take matrix or linear algebra, you'll learn about eigenvalue problems. But that coalescence of those two frequencies occurs at the most difficult computational point. The matrix is what's called defective. And that's the hardest computation to do. Right at the place where you want to know the answer, it's the hardest place to compute. Very, very sensitive to errors in the problem, slight data errors or numerical problems. There's an unending list, it seems almost unending, of things that can go bad with scientific or engineering systems. Here's some classic examples. Some of you may have seen some of these here. Patriot missile, I'll show you what that is. Ariane rocket exploded. Sinking of an offshore oil platform. All these occurred because somebody didn't write the software correctly or didn't understand the limitations of the computer. Patriot missile failure. This occurred a number of years ago, 1991. The Patriot missile was supposed to intercept an incoming missile. I think it was called a Scud missile, and get the Scud missile before it hit the soldiers. But one case, it didn't do its job. So it missed the mark by quite a bit. The Scud missile was not intercepted. Inaccurate computing, misunderstanding of the computer, and the software really wasn't set up to work properly on this somewhat limited computer. The error at a very low level, what it really boiled down to was the fact that certain floating point numbers, like 1/10, that's a nice number, could not be represented exactly in the computer with any number of bits, but this particular computer had 24 bits. And every time we had a tenth of a second, tenth of a second, there was a little bit chopped off at each time. And that tenth of a second kind of built up. I don't really want to get into the total details here, but just focus on this idea of being off a little bit every tenth of a second in the calculation. The computer ran for 100 hours, okay? And every tenth of a second of those 100 hours, you were accumulating a little bit of error. Well, you know probably from the computing course or math course that if we take a tenth, we can represent that, or try to represent it as reciprocal powers of 2, but you never get to the end of the series. The et cetera, it goes on forever now. Anyway, when the clock on the computer was trying to represent a tenth of a second, it only had 24 bits to represent, the zeros and the ones. So it was a little bit off every time that the binary, the error based on the clock ticking every tenth of a second, the error would be 23 zeros and then 1100, 1100. That pattern kept repeating. That's a base 2 fraction. If you convert that to a base 10, it's what? 3 zeros, 3 more zeros. It looks like about 7 zeros and a 9 5. Okay. Every click, every tenth of a second, you're off by that little number. You say, well, that's what, who cares? Well, but you start looking at how that can build up. Take that little tiny number times 100 hours times 60 minutes per hour times 60 seconds per minute times 10 tenths of a second per minute, and you get 0.34 seconds that it's off total if it ran 100 hours. Its ability to intercept then is somehow off by 0.34 seconds. You say, well, 3.3, that's not very much. But the missile that you're trying to hit is coming in at 1,676 meters per second, roughly. So how far could a Scud missile travel in 0.34 seconds? 570 meters. And that's a big distance. If you're here and you think it's over here, 500, you missed by quite a bit. That little tiny fraction that was built up every tenth of a second translated into a big, big miss. And so the so-called range gate was quite outside of the range gate. The computer scientists and software engineers went to work on it, and they improved the code in some places. That was the result. Now, you're sitting out in the desert, and is that very comforting? If you improve the code in some places, I think if I were a soldier out there and said, what do you need? Okay, come on, guys. Let's improved it in some places. No, I want it to be right. Here's a nice one. Well, this is not nice. Big oil rig out in the, I think it was in the Baltic Sea. And in a storm, all of a sudden it crashed and hit the bottom of the ocean. It just fell apart. 57,000 tons sank in the North Sea. When it hit the bottom of the ocean, it hit 3.0 Richter scale. I mean, this hit hard, Why did that happen? Well, there was this computer program, this very nice matrix-based computer code called Nastran, and someone said these supports, they didn't really understand the input data, but they prepared it anyway. And they got some numbers out of it, and they thought, well, yeah, probably looks okay. I've done it, I'll turn it into my supervisor. They were off by 47%, primarily because they didn't understand the input to the computer code. So the whole thing ended up crashing into the ocean. So, not the same thing as a round-off problem or misrepresentation or bad binary bits, whatever, but just because somebody didn't really take the time to read the documentation. Sort of like me with the MATLAB undercut. I didn't take the time to read the documentation. But I did fix my problem. I don't think they fixed their problem.
I know we got killed with your problem.
Right, that's right. So, okay, another problem. This sort of has a negative feel to it, doesn't it? Talking about this bad thing, that bad thing. But there is some lessons here to help some of these things. This is the Rome function that we talked about earlier. And there it is on the board. Term 1, term 2, term 3, term 4. There's 4 terms in it. And we plug in numbers and what's the answer? It's just a math problem. So I was Googling, we should be concerned about round-off error. I think that was the title of the paper I was looking for. But Google thinks we should be concerned about global warming, the data, the climate change, the condition of the earth. I didn't see round-off error coming up in this list at all, but I completed my sentence, and it did say that, okay, well, you misspelled round-off. I think that's right. Round-off with no space. Anyway, this may not be a very popular topic, at least it doesn't come up in Google as a very popular topic, but it's important. Okay, here's the Rome function. Oops, and here's the value we want to plug in. So, Leclerc, he's a computer scientist at College in Charleston. Let's see, how long do we have? To about 4:30 or thereabouts? Is that about
4:30.
Okay.
4:35.
Okay. So anyway, Leclerc wrote a Fortran program to evaluate that function. And what he did was he did single precision, then he did double precision, then he did extended precision, and he was kind of getting it looked like it would converge. Okay, that's the kind of the essence of the paper. Then he gets off into something else called interval analysis. But that's a typical way to do it. Do it with low precision. Do it with a little bit higher. Then hopefully you're kind of converging to the right answer. I tried it too with a Python code. I entered my 2 values, and I did it 2 ways. I wasn't quite sure exactly why I did it this way, but I did it term 1, term 2, term 3, term 4. I did it one way where I used the double star for the exponents, and then I did it again where I just did multiply the star. You know, if I want y to the 6th, then I do 6 y's with 5 stars in between them, and it did the terms. That's commented out, but I did the 4 terms, and then added it up. You know, so output. So I tested my code. I plugged in 1 and 1. I did a little arithmetic, and 226.75. I plug in 1 and 1. So that was my test case. It looked really nice. So, okay, plugged in the real numbers, and I got a number 1.18 e to the 21. That's 10 reduced to the 21 times the 21st. That's a monstrous number. But you look at it and you say, well, it could be. You know, you're taking these kind of big numbers. There's a y to the 6th, and you know, you can kind of see it. Well, there's a y to the 8th, isn't it? So a lot of big numbers going on potentially in here. So tried it another way. I commented out the code with the double star, and I did it with multiplies. Added up the terms. I got 1.17. Wait a minute. I'm different by 21 powers of 10. This time I did a little bit different for exponents. Well, Leclerc, you know, here's his results. He did it single precision. He got 10 to the 29. Double precision 1.17, and then he did extended precision. What do you think? 1.17 something something? Looks like it ought to be kind of close, you'd say. Okay. Use more digits, must be right. So, nothing is right about this. Everything is wrong. But it isn't even right on the sign. It's a minus number. Okay, it's not a plus number. I'll tell you why we know that. Anyway, he went through a very elaborate process, and he showed that it's trapped between minus 0.827 something 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 and something slightly. He gave an interval where he thought the answer should be. Okay, that's nice. You can plug this problem into Mathematica and even MATLAB and do a symbolic, where you're doing so-called exact arithmetic. I tried it in MATLAB with exact arithmetic. Well, I'll try it here, let me see. Well, this summarizes my results. So I got 10 to the 21, where I did double star for powers. I got really different number with the star for powers. Ooh, this was interesting. The third result is when I turned the terms around. I added this to this. I added them up backwards. And you said, why does that change? Term 4 plus term 3, that shouldn't be different, but it's hugely different. And you can get any answer you want, depending how you program that assignment statement, which is just extremely disturbing. But I do believe using Python with integer arithmetic. I figured out a way to do this with integer arithmetic. And you can get a minus 0.827 something, which I do believe would be the correct answer. I'll show you how Python is really kind of neat in this regard. First of all, MATLAB, I got MATLAB on my home computer. I was talking to Dr. Andrews about the perks at Wright State when I retired. I got a library card, but I also did get a license to MATLAB, which I have on my home computer. So I did MATLAB, and I did it symbolically. Ooh, this is full precision, every single digit that's possible for the data here. Val 1 represents term 1, val 2 is term 2, val 3 is the value of term 1, 2, 3, 4. If you add val 1 to val 2, you get a number which is almost the opposite of val 3, but it's off just a little bit. Huge number of digits, 50, red number, 48. The first three terms add up to minus 2. But you can't discern that using floating point arithmetic. Val 4 is easy, it's just x over 2y, that's easy. But it's those first three terms where the first and second combine to a big number which is opposite in sign but almost exactly the same as the other one. And that's really where this problem is difficult, because we're adding large numbers of different signs which are almost the same. So the so-called IEEE 574 floating point arithmetic, that has huge problems with adding those first three terms. But what you can do in Python, Python has integer data type. You say, well, this is floating point. Well, you can turn it into an integer problem by multiplying it by 200y. It'll clear out all the fractions, and you can just then go full bore with as many digits. Python will bring in as many digits as it needs. And I got it exactly, to 16 decimal places, exactly correct. So I was really proud of Python. We kind of, at times, will say negative things about Python, but this precision, if you can recast your floating point problem in terms of integers, and then Python will let you have as many digits to your integers as you need. Well, within memory, speed limitations, I suppose there are some ideas there. Anyway, that's the wrong function. Another idea that's useful, if I had a algebra problem. Well, there it is, equation 1. That numerically is hard to evaluate when h is really, really big. 10 plus 1 over a big number is 10 plus a small number, and I subtract that from the, you're going to get a 0 almost every time if you do that. But a little bit of trickery here, and not really trickery, but just if you multiply and divide by, I call it the conjugate, I'm not sure what to call that thing, but where you change the sign from a minus to a plus, and then you're dealing with the difference of square roots, and the algebra works out that equation 3 is really the better equation. We manipulated equation 1 so you were not subtracting almost equal numbers. Watch out for subtracting almost equal numbers. Very, very bad. A little bit of a calculus problem. This is from the Pitfalls in computation. Why the math is done. There's nothing wrong with the math. It's just when you code certain things, they don't work out the way you wanted it. Let's say I had e to the x, and I wanted to evaluate e to the x. There's the series on the left, but I want to evaluate it at a negative value. Well, what do? You realize all of a sudden you've got an alternating series. I got a 1, I got a minus, I got a plus, I got a plus, minus, plus, minus, plus, minus. That is really, really bad. Something called numerical smearing. The plus minus pattern, these numbers are just not adding up. You have an alternating series, be very, very careful if you try to add lots of terms. 004 was the answer if you use Python and bring in the exponent, but if you just try to add it up, you get 002, so you're way off on the value. What's the numerical answer here? Don't do it that way. Instead of e to the minus 0.55, write it as 1 over e to the 5.5. That way you've got a series in the denominator which adds up very nicely. You don't get this plus minus destroying the answer. That just works out really great. Algebraically equivalent, but very much different numerically. In computing the sum of things, I guess what works really nice is you want to avoid the so-called catastrophic cancellation. Sort the numbers from small to large. Add up the small numbers first and then add the big numbers if you want to get a good total tally on the numbers. Break up the list, maybe even break out the negatives and do those separately, do the same thing. But just a random list of numbers, you're going to get into the same numerical issues as with an alternating series. It just does not add up right. Here's a little program we wrote. Got some small numbers and got some large numbers. Got small number of size 1 e to the minus 7, so 1 times 10 to the minus 7, a little tiny number, and I got 10 million of those. And I got large numbers, 10 to the 11th, I got 10,000 of those. I've got 2 loops. One loop is adding up the large numbers first, and then continues the summation on that, and the small numbers coming in after the big numbers. Mathematically, one would say, well, there should be no difference. Then I did it again with the small numbers first, and then the big numbers second. Back this out. So there are 10 to the 7th small numbers of that size. There are 10 to the 4th large numbers of that size. If you add up all the small numbers, they add up to exactly 1. If you add up all the large numbers, 10 to the 15th, if I counted the zeros correctly. So the right answer ought to be the bottom line. But if you do the big numbers first, that little tiny 1 compared to the really huge number, it just gets wiped out by the precision of the, necessarily the floating point precision is not such that it can even see that number. But if you add up the little ones first, take those into account first, and then add them to the big ones, you're going to get a much better total. There are ways to optimize a loop to avoid that. William Kahan, who retired from computer science department at Berkeley, I was looking at a paper where he shows how to anticipate that, how to write your loop so that it does anticipate when you are getting into this big, small issue, and kind of a clever little loop. So a lot of things can happen, a lot of things can go wrong with computing, but a lot of things go right. Normally things go well. Normally commercial software is just fine, but you never know. The rump function, you do that, you debug your code, you run test cases, you do everything right, and your answers are off by 10 to the 21 power. Just blows you away. And then until you dig a little deeper, dig deeper. Don't take the first answer to be correct. Dig a little deeper. So that would be certainly a good lesson here. So anyway, we've covered a little bit about computational science, some of the engineering problems, and then looked at some of the ways that computing can go wrong at times.